So to find the inverse Laplace transform, we need some tools and techniques, and today we will see some methods for computing the inverse Laplace transform for a given function. So the first method is using tables of Laplace transforms of known functions. So for example, you know the Laplace transform of sine t, cos t, e to the power alpha t, etc., minus alpha t, etc. And if you are given a function in S, such as S over S square plus 1, then you can immediately know that it's the Laplace transform of cos t. So we have computed the Laplace transform for many elementary functions like this, and if you are given our function is in a known form, then we can immediately look up its inverse from a table of known Laplace transform of known functions. So this is the first method, which is the most basic, which is to just go and look it up on a table of known functions and find if it's there or not. So in case it's not there, then you go to the second method, which is using the properties of the Laplace transform to reduce the problem, so that the first method, so that method 1 can be applied. An example for this method is to compute the inverse Laplace transform of, say, the function log of 1 plus s. Now we note that the derivative of this function log of 1 plus s is simply 1 over 1 plus s. And so if we take the inverse Laplace transform on both sides of this equation, ln 1 plus s is the inverse Laplace transform of 1 over 1 plus s, which we know, and this can be, you can look it up on a table, and this is e to the power minus t. So the inverse Laplace transform of the derivative is e to the power minus t. On the other hand, we know that this is equal to t ft with a minus sign, because multiplication by t gives you minus times the first derivative of the function. So therefore we have ft equals minus e to the power minus t over t. So we have used one of the theorems for the properties of Laplace transforms to convert our given function log of 1 plus s to a known function which is 1 over 1 plus s, and then we can look it up in a table, or we can simply compute it by hand to get our answer. The third method is the method of partial fractions. And this is one of the most widely used methods to compute the inverse Laplace transform. So here what I mean by a partial fraction is that we begin with a function fs. So the problem is to compute L inverse of fs, where fs is given by a quotient ps over qs, where ps and qs are polynomials in S, with the degree of p less than the degree of q. So in this case we have some explicit methods and we can write PS by QS in the form such as 1 over S plus alpha 1 plus A over S plus alpha 1 plus B over S plus alpha 2 plus so on, and let's say E over S plus alpha k, and here A, B and E are all constants, and so these are called the partial fractions. These are called partial fractions. So now that we have reduced the form of PS over QS in this form, then we can apply the linearity property of the inverse Laplace transform. So the inverse Laplace transform of PS over QS is then e to the power A times e to the power minus alpha 1t plus B times e to the power minus alpha 2t and so on, plus E times e to the power minus alpha kt. So by reducing our problem again, but this time to a very easy form, which is some constant over S plus another constant, we can immediately find out what is the inverse Laplace transform. Of course, we cannot always do this, it is just one of the forms. So this is, for example, we can find out in this case where PS by QS can be written in such a form. There are other forms of partial fractions which we will look at, but the idea is the same, which is to convert the function PS over QS in a simpler form where we can know explicitly the inverse Laplace transform. So the method of partial fractions is simply to know these constants A, B, etc., and then we can apply this, simply applies this linearity formula to get the inverse Laplace transform. So this is one of the most important methods. The fourth method is the so-called convolution theorem. Which asks you to compute the inverse Laplace transform of a product of two functions fs and gs, where the inverse Laplace transform of fs and the inverse Laplace transform of gs are both known. So the convolution theorem gives you an explicit formula by which you can compute the inverse Laplace transform for the product of two Laplace transforms, and then you can compute the inverse Laplace transform using the inverse Laplace transforms of fs and gs. Last but not the least, this is the complex inversion formula. This is a direct method to compute the inverse Laplace transform for a given function fs using contour integration in complex analysis. So although this is one of the most powerful methods, because it gives you a direct formula to compute the inverse Laplace transform, we won't cover it. This is out of our scope for this course, because we do not assume the knowledge of complex analysis, so I won't cover it in this course, but nevertheless it is one of the most important direct methods to compute the inverse Laplace transform. So this we won't cover. So the first four we will cover in this course, and we will see how to compute the inverse Laplace transform using these methods. So let's go back and see what the first two methods were. The first one is simply looking up tables of Laplace transforms of known functions, and if you find your function which you want to find your inverse Laplace transform, and if you find it in your table, then you're done, because you don't have to compute it by hand. Otherwise, if you don't find it there, then you have to use some other method. So the other second method is to use the properties of Laplace transforms to reduce it to an easier problem, in which case you know what is the inverse Laplace transform of your given function. The example I gave here is quite illustrative here, because you don't see immediately what is the inverse Laplace transform for the log function, but once you take the differential, you immediately see that it is of one of the known forms, and then you can immediately find the inverse Laplace transform of it. So of course here we can use all the basic properties that we have covered of Laplace transforms, starting from linearity, change of scale, first translation, second translation, multiplication by t, division by t, and then we have the derivative theorem, then we have the Laplace transform of integrals, and all these properties that we have seen we can use in this method too. So I'm not going to explicitly redo more examples in this method. We will see it as we go along, and in fact our third method is quite related to the second method, because we are again reducing our problem to computing the inverse Laplace transform of simpler functions. In this case they are partial fractions, and we will cover in much more detail this method, and of course we will also cover the convolution theorem. So these two will be the main focus for our methods to compute the inverse Laplace transforms. So let us begin with partial fractions. Partial fractions. So as I said, the problem is to compute the inverse Laplace transform of functions of the form Ps over Qs, where Ps and Qs are polynomials, non-constant polynomials in S, with degree of the polynomial Ps is strictly less than the degree of the polynomial Qs, and we also assume that Ps and Qs do not have any common roots. So it's a sort of a reduced form for a quotient of polynomials, and these kinds of functions are known as rational functions. So here we would like to break our form for our Fs, and according to the form of Qs we will give a different expression for our partial fraction. So let me give you a table. So factors in Qs and partial fraction expansion. So the first case is what's called a linear factor, if you have a linear factor of the form as plus b in Qs, where a, b are constants, then the partial fraction expansion for this is given by a over as plus b. So we have to determine this constant, this coefficient a for this partial fraction expansion for each linear factor of this form as plus b. The second case is we have a repeated linear factor, meaning that we have some power as plus b to the power n in Qs, and again a and b are constants and for this the partial fraction expansion is given by a1 over as plus b plus a2 over as plus b whole square plus, and you have a sum up to n, because this n is our exponent in the repeated linear factor. So in the end you have as plus b to the power n. So the partial fraction expansion for a repeated linear factor in Qs is this sum. This can be written as sum over ai over as plus b to the power I equal to 1 to n. So this is the partial fraction expansion, and we have to do this for each repeated linear factor in Qs. So we can have multiple such repeated linear factors. Same for the first one, we can have multiple linear factors, multiple repeated linear factors, or mixtures of those, but for each such factor in Qs we have to use the partial fraction expansion on the right hand side. The third one is a quadratic factor of the form as square plus bs plus c. So here, all constants here are I assume that, for example, a is not equal to 0. Here also a is not equal to 0, and here I assume a is not equal to 0 as well as b is not equal to 0. So in this case, for each quadratic factor we have the expansion as plus b over as square plus bs plus c. So if you have a quadratic factor, you have an extra term which is a linear function in S. Earlier, if you have linear factor or a repeated linear factor, you did not have any term in S, you only had constants, but now you have terms in S as well. And so this is the third one. Lastly, if you have a repeated quadratic factor, then we have, so suppose we have as square plus bs plus c to the power n, then the partial fraction expansion is very similar to the repeated linear factor, and here you have a sum from I equal to 1 to n, and you have ais plus bi over as square plus bs plus c to the power I. So these are the forms of partial fraction expansions for each of these cases. You can have other cases as well, but we will restrict our study to only these kinds of cases. And in many examples, you can reduce higher order factors to lower order factors using some factorization method, and then you can apply these partial fraction expansions that you know. Okay, so let's see some examples. So for the first example, we will take fs to be 1 over s minus a times s minus b. So here this is our PS is 1, so PS can be a constant polynomial, but QS is not a constant polynomial. This is s minus a times s minus b. So for each linear factor in QS, we have two linear factors. These are linear factors. So for each linear factor, we will write PS over QS. So for the first factor, s minus a, we write it as a over s minus a. And for the second factor, similarly, we write b over s minus b. So this is our 1 over s minus a times s minus b. And now we can multiply throughout by s minus a times s minus b, and then you will get an identity in S. This is of the form a times s minus b plus b times s minus a. So this is an identity in S. So this is true for all values of S. So both sides are both sides can be expressed as polynomials in S, and this identity holds for all values of S. So we can plug in values of S on both sides to find the constants a and b. Constants a and b. So let's do this. We have 1 equal to a times a s minus a plus b times s minus a times s minus b, b times s minus a. So if you put s equal to b, this implies 1 equal to b times b minus a, which implies that b equal to 1 over b minus a. Similarly, you can put s equal to a. This implies that 1 equal to a times a minus b, which implies a equal to minus 1 over b minus a. So then we can write 1 over s minus a times s minus b as minus 1 over b minus a times 1 over s minus a. So this is our a, and we have another term 1 over b minus a times 1 over s minus b, and this is here our b. So now we can immediately compute our inverse Laplace transform for this function fs, and this is nothing but a times exponential at plus b times exponential bt, where a and b are as above. So we know explicitly the values of both constants a and b. So this is valid for t greater than or equal to 0. So in this case, we can find quite easily the partial fraction expansion and the resulting inverse Laplace transform. So you can have, let's have another example where you can have something like s plus 2 over s minus 1 times s plus 5. So here your PS is no longer a constant, and QS is s minus 1 times s plus 5. So again you have only linear factors. So in this case, our partial fraction expansion will be of the form a over s minus 1 plus b over s plus 5, and again a and b are constants. So this is our s plus 2 over s minus 1 times s plus 5. So again multiply on both sides by s minus 1 times s plus 5. So you get s plus 2 equals a times s plus 5 plus b times s minus 1. And now this is our identity in S. So this is true for all values of S, so you can plug in whichever value of S you find suitable and solve for these constants a and b. So let me take S equal to minus 5, so this will make this factor go away, and so this implies that b times minus 6 equals minus 5 plus 2, which is minus 3. So this implies that b equals half. And then if you put s equal to 1, then this factor goes away and you will get a times 1 plus 5 equals 3, which implies that a equals half again. So both a and b are half. So this implies that L inverse of fs, L inverse of our given function fs is half times exponential. So this is, we have two constants here. This is our a and this is b, but b is taken to be minus 5, so that we have term of the form s minus b, and here we have s minus a. So a equal to 1, and b equal to minus 5. So we can immediately write this as half times e to the power at, which is just e to the power t, a is 1, and then half times e to the power bt, which is minus 5t. This is valid for t greater than or equal to 0. So here we have a non-constant polynomial in the numerator, but we can still find out what is the partial fraction expansion. So I'll try to simplify this process when you can multiply on both sides by the denominator qs and plug in one by one. So this is called the Heaviside's cover up method, or also the Heaviside's expansion formula. So this method can be applied when qs has only distinct linear factors, e.g. something like s minus a times s minus b. So for example, in our last example, ps by qs, this was s plus 2 by s minus 1 times s plus 5. So the Heaviside's cover up method is to cover one of the linear factors. So let's say the first one. So let me cover it. So we have covered this linear factor, and what we get is this. Function s plus 2 over s plus 5, and simply take the limit as s goes to 1 of this new function. So you're covering up one factor and just taking the limit of this of s as s goes to this factor's constant, and evaluate for the function when you cover it up. So in this case you will get 3 by 6, which is half. So this gives you the value of a, and this is in the partial fraction expansion. This can be written as a by s minus 1 plus b by s plus 5. And similarly, if you write again s plus 2 by s minus 1 s plus 5, and you can cover up now this one. You can cover up the second factor and evaluate the limit as s goes to minus 5, s plus 2 over s minus 1, and this is minus 3 over minus 6, which is again half. So this gives you b. So therefore we can find that we have half times s minus 1 and half times s plus 5. So this is just a simple example to illustrate that how to cover up one of the factors and take the limit for the resulting function. So that this is the Heaviside's cover up method, and let me write this as a theorem. Heaviside's cover up method for rational functions with QS having only distinct linear factors. So we have some function fs, ps over qs, qs as above, so it has only distinct linear factors. So let's suppose that qs can be written as s minus alpha 1 times s minus alpha 2, s minus alpha k. Alpha k's are all distinct numbers. So here alpha k's, note that alpha k's can be real as well as complex. So I will give an example where you can complex factorization. So in this case, when you have such distinct linear factors, then fs has a partial fraction expansion fs equals sum ai over s minus alpha I from 1 to k, and ai is given by, it is the limit s tends to alpha I, s minus alpha I multiplied by ps over qs. Now note that since alpha I is not a root of ps by our assumptions, because ps and qs do not have any common roots, this is the same as p alpha I over q prime of alpha I, assuming that q is differentiable at alpha I, which is true here because q has only distinct linear factors and it is a polynomial in S. So each ai can be directly computed by this formula. You just plug in alpha I for p and you plug in alpha I for the derivative of q. So this is the Heaviside's cover-up method for rational functions where the denominator has distinct linear factors. The Heaviside's expansion theorem is a corollary as a consequence of this theorem, which says that the L inverse of such a function, so fs as above, then the inverse Laplace transform of this function is simply the sum I equal to 1 to k p of alpha I over q prime of alpha I multiplied by e to the power alpha I times t, and this is immediately obtained from the partial fraction expansion, and this is valid for t greater than or equal to 0.